Hi Pre-Cal Honor. So this is 2.5 to 2.8 extensions. This is the last problem. We are going to design a soda can. Okay, so again, 2.5 to 2.8 extensions, part 1. Okay, so you're the designer now. So what we're going to do is we need to design a can, let's say for juice or pop or something. And if you think about it, if you were really going to design a can, if that was your job, you would have some parameters. So the first parameter that we have to have a volume of 1,000 cubic centimeters. Okay, and our can has to be a cylinder. So first of all, think about, the base is a circle, so there's a radius, there's a height, etc. And we want to minimize the surface area of the can, which if you think about it, that would make sense. Because, again, the sugar water, like if it was a Coca-Cola or something, the sugar water that goes inside the can is a lot cheaper than the actual packaging. So again, we're going to minimize the surface area to maximize our profit. So first of all, volume is area of the base times the height, and the base is a circle. So we know that 1,000 equals pi r squared times h. So you can write an equation for the height in terms of radius. So what I would like you to do right now is pause the video and write an equation that would describe the surface area of the can. So again, there are two bases that are circles, and then the lateral area. Come back or think back to geometry, if you would. Like if this was a label on a soup can or something, how you would unwrap it. And so the lateral area is actually of the can, of a cylinder, actually is a rectangle. So go ahead and think about the surface area of the can. Pause the video, please. So the surface area is 2 pi r h. That's the lateral area, plus there are two circles with the bases are both circles. So 2 pi r squared. So now I'm going to let h be 1,000 over pi r squared. So I have an equation for the surface area in terms of radius of the can. So we're going to grab our calculator right now. Let's go ahead and do that. Go ahead and pause the video, graph this in your calculator, and find the minimum surface area. So again, the graph's going to look something like this, and we want what radius will give us the minimum surface area. Go ahead and pause the video and do that now, please. So for a window, I chose 15, and again, 15 centimeters for a radius of can, that'd be quite large. Okay, I just went really, really large. And then I just chose the surface area to be 1,000. I just wasn't sure what to pick. I just picked, again, you probably, if you wanted to, could pick a number for r that made sense, something nice and easy, like let r be 10, and then substitute it back into that equation to get something that would make sense for y, if you're having trouble finding a window. If you take a look at the graph, that's a pretty good window. And now we're going to use the minimum feature. So if you choose minimum, and you're going to go left of the minimum and right of the minimum and try and find that radius that gives us the minimum surface area. Because again, the sugar water that goes in the can is cheap. It's the packaging that would be expensive. So again, you might want to, if you were designing a can, you might want to try and maximize your profit by minimizing the surface area. Okay, so now if we find the minimum surface area and the radius that goes along with it, there you go. So 5.42 when the surface area is 553.58 square centimeters. Okay, so if you think about this then, what we're going to do next, radius is 5.42 centimeters with the minimum surface area. We could use our formula for h to find the height that corresponds to that, 10.84. But now there's another parameter. So again, the design team now has to find the radii, or the ranges of radii and heights that can be used. But here's another parameter. We must use between 600 and 900 square centimeters of aluminum. So now we're going to go back to our calculator, and we're going to let y be 900 and 600, and we need to use intersect to find these points. So we need to find the corresponding radii and heights of the can, the dimensions, okay, that would correspond with 600 and 900 square centimeters of aluminum. So go ahead and pause the video. Go ahead and use your calculator and find those points, please. So we go back to the calculator. Let y be 600 and y be 900. So we need to find what values of r would be within those parameters. So again, looking at the calculator here, I need to find these intersection points. Okay, so we went ahead and did that, and we found that this x was 7.13, this x was 10.65, this x was 2.31, and this x, it was 4.007 centimeters. So again, we know that all of these R values would be within our parameters. So you could use your equation for h that we used earlier. H is 1,000 over pi r squared to find the corresponding heights. And again, now we're just trying to think about what would be the dimensions of our can. So let's go ahead and take a look. So again, here I wrote them down for you. So notice, let's see. So notice these R values would be within our parameters. So now if I wanted to use R values between 2.3 and 4.07, notice I could go ahead and find the corresponding heights. That would be a tall, narrow can. Or if I use the radius between 7.13 and 10.65 and find the corresponding heights, again, that would be like a shorter, wider can. So now you just have to think, what would make the most sense? And again, I think I use the radius of 4.07 with a corresponding height of 19.825, because again, otherwise the can is too wide or too tall to be practical. It would be hard to hold it in your hand, wouldn't necessarily fit in the cup holder. We got to think about vending machines and things like that. So again, the design team, you did a great job with your parameters of a volume of 1,000 cubic centimeters, and it had to be a cylinder, and your surface area had to be between 600 and 900 square centimeters of aluminum, and you went ahead and found the dimensions of the can. Great job, everybody.